Okay, so today we're talking about properties of gases. This is probably a review because I know a lot of high schools do gases as part of their curriculum. So I think most of what we're doing today is going to be a review for a lot of you. So let's just review some of the physical properties of gases. They experience no IMFs. Well, we say that. Technically they do. In a couple lectures, we'll talk about the IMFs that they do experience. But for right now, we're just pretending that they experience no intermolecular forces. But just bear in mind that in reality they do experience IMFs to a small degree, and we'll factor that in a couple lectures. A gas is mostly empty space, right? That's why you're able to compress a gas, because the gas particles are spread far away. And so when you compress a gas, you're just smushing them closer together, right? Gas particles move independently of each other. So each particle is moving independently in straight lines. And then they only change direction when they collide with either each other or the walls of their container. Okay, so this is all kind of basic properties of gases. I'm assuming that you probably remember from high school or physical science or other courses. All right, some vocab we need to talk about. Diffusion. I know you know this from biology, and the definition you learned for biology works the same here, right? It's movement from an area of high concentration to low concentration. So the gas is spreading out. Right, so if you have a gas over here, and then this side's completely empty, you turn the valve, the gas spreads out. Okay. So if I spray some perfume up here at the front, it's an area of high concentration. Only I would be the one smelling it initially, and then it would spread to the whole room, and you guys can all smell it. That's diffusion, right? Area of high concentration to an area of low concentration. And then effusion, with an E, is escape through a tiny hole. Okay. So if you puncture your tire, or you puncture a balloon, right? Those particles bounce in all randomly, and then eventually they will bounce through that hole, right? That's effusion. Diffusion versus effusion. Okay, so escape through a tiny hole. Do we remember these vocab words while I eat my second breakfast? Okay, now the rate of diffusion, and the rate of diffusion too, is determined by size, but it's also determined by temperature too. Okay, you can only compare rates if they're at the same temperature. I'll show you how to compare rates at different temperatures in a minute, but it's easier to compare them at the same temperature, right? Because temperature, by definition, is a measure of kinetic energy. And so if one gas has a lot of kinetic energy because it's at a high temperature, the other gas doesn't have as much, it's not an easy comparison if they're at different temperatures. But I will actually show you, this is kind of not true. This is kind of a not true statement because I will show you how to do it at different temperatures. But right now, we're only going to look at the same temperature. Okay, so smaller gases diffuse faster than large gases. Right? Large molar mass is going to diffuse at a slower rate than low molar mass. Now, like I said, this is kind of a lie. You can only compare at the same temperature. That's kind of a lie. Right now, you only know how to do it at the same temperature, but in a couple minutes, I'll show you how to do it when we're at different temperatures. So, primarily, we're looking at the effective size right now. And then in a few minutes, we'll look at temperature. So let's look at two balloons. All right, this balloon is filled with nitrogen gas into this balloon is filled with helium gas. Gee, how come this one is not floating? They're filled to the exact same volume. I don't know what that volume is. Let's just pretend it's 1.5 liters. Okay, how come this one is not floating if they're both filled with gas to the same volume? Why is the N2 balloon not floating? The helium balloon is. We're going to do this in a couple lectures, so I might as well introduce it now. Why is that? Why is the helium balloon floating and the nitrogen one isn't? Right, right. Think about the molar mass here, right? Helium's molar mass is 4, N2 is 28, right? And you think about relative to the air. Okay. Now these are filled to the same initial volume. Let's just pretend 1.5 liters. I don't know what it is. And then we puncture a small hole in each one of these. We go away for 5 hours and we come back. Right? The helium balloon has significantly shrunk, right? So much so that it's now sitting on the ground, right? That means that we've replaced some of that He with other stuff. Whereas the nitrogen balloon pretty much looks the same. Why? Why? Well, significantly larger molar mass, right? Significantly larger molar mass. And this is an experiment that I actually had my students do as a home chemistry assignment a few years ago. They did it at home, kind of like the experiment you guys did yesterday, a home experiment. This one we did at home. They got balloons, and you can go to you know, like a florist or grocery store and have a balloon filled with helium, right? You can fill one yourself, so you're not filling it with helium. You don't exhale helium, right? And so if you put a piece of tape, you can try this. If you get a piece of Scotch tape and you put that on a balloon, and then you put a needle through that Scotch tape, it won't pop the balloon. If you stick the needle straight into the balloon, it'll pop the balloon, right? But if you have a piece of tape on it and you puncture the balloon, it'll maintain that pressure and it won't pop the balloon. And so if you do this experiment, you puncture both balloons the same size and you just watch what happens, right? This is an experiment that I've actually had my students do before as a home experiment. And you can do it for yourself this weekend if you want. So low molar mass is going to diffuse faster than high molar mass. So here's just a comparison, right? There's H2, very low molar mass. This is what gives bananas their smell. It's also what gives pears their smell. If you take the organic class next semester, the elementary organic, you'll learn how to name this and draw this. Okay, so large molar mass versus small molar mass. And then here's some data to represent this too. Okay, here's the relative number of molecules with a given speed, and then here's the speed. Right, so average speed here, average speed here, average speed here, average speed, average speed. Right, the average speed for the low molar mass is the highest, then helium, then water, then nitrogen gas, then oxygen gas. That makes sense, right? Larger molar mass means it's got a lower speed. And so we're going to quantify the differences here using Graham's law. This is a really easy calculation. Now again, we're doing this assuming that they're both at the same temperature. Okay, we're not going to look at different temperatures right now. We'll do that in a couple minutes. But if they're at the same temperature, you can use Graham's law. And so here's Graham's law. It's molar mass of B over molar mass of A, where B is the heavier one. Okay, so the one with the higher molar mass goes on top, one with the lower molar mass goes on bottom, and then you just take the square root of that. Okay. And this gives us the ratio. How many times faster A is going than B? Now again, we're assuming that this is at the same temperature. I'll show you how to do it at different temperatures in a couple minutes. So this is a very easy calculation, right? No stoichiometry here. It's just molar masses, excuse me, and then taking the square root. So what about, let's do this one. Calculate the ratio of diffusion rates for H2 and UF6. Okay, before I even pick up my calculator, I know that's going to be a pretty big number, right? Excuse me, because H2 is going to have a molar mass of 2.016, right? Uranium hexafluoride is going to be a lot larger than that. So which one's going to go on top, the molar mass of H2 or the molar mass of UF6? UF6, right? 352 divided by 2, and then take the square root. That gives me an answer, 13.2. What does that mean? What does that 13.2 tell me? That means that H2 is diffusing 13.2 times faster than UF6. Okay? That's a reasonable answer given the extreme differences in molar mass. Right? You would expect this to be going a lot faster. 13.2 times faster is what Graham's law is telling us. How many times faster the smaller gas is going than the larger gas? Does this make sense? You're going to try one in just a second. If you get an answer like 0.004, you know you did your ratio backwards, right? It's going to be a number greater than 1. Heavier one's going to go on top. Why don't you try this one? How many times faster will helium gas diffuse than nitrogen gas? I'm not even going to pause the recording here. This is going to take you Just a couple seconds. Got an answer? I came out with 2.7. Did you? Don't forget that nitrogen as gas is diatomic, right? So it's not 14, it'd be 28 as its molar mass. Nitrogen gas is diatomic. It's reasonable, right? Because the mass difference between 4 and 28 is a lot closer than it was between 2 and 350. Okay, I will pause the recording for this one because you might have to think a couple minutes. Hydrogen gas diffuses 15 times faster than a mystery gas. What is the molar mass of that mystery gas? I'll pause this one so you can have a few minutes to think. All right, so let's look at how this question is worded. We're being told that hydrogen is diffusing 15 times faster than a mystery gas. So if we're setting this up, we're going to have the square root of something over something, right? Is hydrogen going to be the bottom number or the top number? It'd be the bottom number, right? Because I'm being told that it's 15 times faster. So that means I'm going to have the square root of x over the molar mass of hydrogen. And then what am I going to set that equal to? Equals 15, right? Now what if I said hydrogen is diffusing 15 times slower? Then the molar mass of hydrogen would be the top number, right? Of course, it'd be hard to have something diffuse slower than H2, but let's just pretend for the sake of argument, right? So the molar mass of the mystery gas, we're just going to call that X over the molar mass of H2 equals 15. Okay, so now we just plug in. I came out with 454 grams per mole as my mystery gas. Did you? Somewhere in that neighborhood? Because we had the square root. To get rid of that square root, we had to square both sides. Yep. Does everybody understand how to do one like this? Your homework on gases, which will go up on Monday, will include a problem like this. So you've got homework due tonight. I'll let you have a weekend homework free. How about that? All right, so like I said, gases and temperature. Temperature is a measure of kinetic energy. I think I told you this story with my 4-year-olds. They still remember, you know, when I give them their cup of water and it's cold, they say, "Mom, this has low kinetic energy." I'm like, that's right, it does, right? Particles in the gas, particles in their liquid that are cold are moving, and they'll go slow, right? So we talk about kinetic molecular theory at my house a lot. So temperature is just a measure of kinetic energy, right? Higher temperature, moving faster. And especially if we're talking about the gas phase, that's not going to be different in the gas phase than it will be in the liquid phase. Right? When you're talking about gas at a high temperature versus gas at a low temperature, one's going to be moving significantly faster just due to the fact that it's at a higher temperature. So in these Graham's law ones we were doing just now, right, this is all at the same temperature. But what if I gave you two temperatures, two different gases, two different temperatures? Well, now we'd have to factor temperature into our calculation, right? Because it would not be fair to compare a really high molar mass gas at a really high temperature versus a really low molar mass gas at a really low temperature, right? There wouldn't be comparable if we didn't have the same temperature. So because speed increases with temperature, right, we have to factor that in as well. Now let's just, before we do the math, let's pretend that all of these are at 28 degrees Celsius. All of these are at 28 degrees Celsius. Could you rank these without doing any math? They're all at 28 degrees Celsius. Could you rank these in terms of increasing speed without doing any math? Yeah, you could. How would you do it? If they're all at 28, molar mass, exactly. Just go by molar mass, right? Now, you also could have calculated root mean square velocity, which is what we're doing now, right? What if we have two different temperatures? So here's what we do if we have temperature involved. Notice T is part of this problem. It's part of the formula here. This is called the root mean square velocity. And so this is calculated by taking the square root of 3, 3 is just a constant, and no units associated with the 3, times R, which is 8.3145 joules per Kelvin mole. Okay, there's another R coming up soon. We do gas calculations, it's different, so make sure you're watching your R's. T is temperature in Kelvin. So if you have a Celsius temperature, how do you convert that to Kelvin? Who remembers? Add 273, right? And then watch this. This is not molarity. This is not molality. This is a funny cursive M. It's molar mass in kilograms per mole. Kilograms per mole. Why on earth would I convert my molar mass from grams to mole to kilograms per mole? That just seems like a complete waste of time. I'll show you why you got to convert it to kilograms per mole. It makes our units work out. Okay, if our mass is not in kilograms per mole, then our units in here turn into a train wreck. So I will show you why this molar mass needs to be in kilograms. We're gonna figure out what the units of this will be. I think you already know what the units are gonna be. Who wants to take a guess what the units will be here? For root mean square velocity. Anyone want to guess what those units will be? Meters per second, right? I'm going to show you how you get meters per second out of all this mess. The way you do that is because your mass has to be in kilograms. Otherwise, it's a mess. Your units are just a disaster. So make sure your molar mass is in kilograms per mole, not grams per mole. Root mean square velocity. Okay, so we use this when temperature is part of the picture. When we were using Graham's law, right, we were assuming they're both at the same temperature, so it didn't matter. Here, we're calculating at a specific temperature. So now we can compare two gases at two different temperatures. So let's talk about the units. How do I get meters per second out of all this mess? Well, the way we do it is we need to remember back to physics, okay, those of you who are in physics currently, that a joule is 1 kilogram per meter squared second, 1 kilogram meter squared per second squared, right? 1 kilogram meter squared per second squared. That's something that we learned in physics, yes? Okay, so if we've got 3 RT over M, now remember R is joules per Kelvin mole, okay, so we're just gonna substitute everything in. 3 is a constant, so we can ignore it, it doesn't have units. So joules per Kelvin mole, that's R, and T is Kelvin, times kilograms per mole, divided by kilograms per mole. Right, we just substituted into this. Now, we remember what a joule is. A joule is a kilogram meter squared per second squared, times, per kilogram per mole, kilogram mole, times Kelvin. Right, so we're just substituting this in right here, being divided by Kelvin mole times Kelvin. Right, and then this is still the same denominator. We just substituted the definition of a joule in right here, divided it by Kelvin mole times Kelvin. And now we're just going to do some reduction. Look, all our kilograms go away, our moles go away, our kelvins go away. So that leaves us with the square root of meters squared per second squared, which obviously would be meters per second. Okay, so if your mass, I'm not going to make you derive this on a test. That's not really a useful exercise. But the reason why I show you this is to emphasize the point that if your mass here is in grams per mole, right, that means that when you get down here to this step, these kilograms don't cancel out. You'll have kilograms per gram, which won't make sense. Okay, so I'm not going to make you derive where the units come from. I show you this so you can understand why the mass needs to be in kilograms per mole instead of grams per mole. Because I feel like if you know why you're doing it, it's easier to do, right? If you're just doing it because I say do it, that doesn't have a whole lot of meaning. At least to me it wouldn't. So let's calculate the RMS velocity for helium gas at 45 degrees Celsius. So here's our formula. Square root of 3RT over M. And I put it in that funny cursive print to distinguish it from molarity, distinguish it from molality. It's neither of those, right? It's molar mass in kilograms per mole. So if the molar mass is 4 grams per mole, that would be 4 times 10 to the negative third kilograms per mole, right? We've moved the decimal 3 to the left. 1, 2, 3. Excuse me. So, plugging in, 8.3145 is R. Kelvin temperature, 318, divided by 4 times 10 to the negative third. Take the square root. That gives me our answer. I mean, is that a reasonable speed? Is helium a large gas or a small gas? It's small, right? Helium gas is small. If you get something like times 10 to the negative 6th meters per second, is that reasonable for a gas? Probably not. I'd check my work. So I'm not going to make you derive where the units came from. I just want you to understand how you get those units so that your final answer will include the correct units. Do we agree? You ready to try one? Okay, what about this one? Which is faster, carbon monoxide at 25 degrees Celsius or carbon dioxide at 425? So 2 different gases, 2 different temperatures. Which one's faster? See what we got. So we've got a pretty significant temperature difference here, right? 25 degrees Celsius versus 425 degrees Celsius. We've got carbon monoxide versus carbon dioxide, right? So 2 different gases at 2 different temperatures. So Graham's law won't work here, right? Because we're at 2 very different temperatures. So for carbon monoxide, I got 515. For carbon dioxide, I got 629. Did you? And it's, you know, if these are at the same temperature, if they're both at 25, who would be going faster? If they're both at 25, or if they're both at 425, if they're both at the same temperature, who'd be going faster? Carbon monoxide, right? Because it's a significantly lower molar mass. But because we've got this severe temperature difference. The reason I picked 425 is because I had to pick an extremely high temperature to even get this one to be higher. Because if you're at temperatures like, you know, one's at 25 and one's like 100, carbon monoxide still comes out faster. And I wanted to find an example where the heavier one was going faster. I had to go all the way up to 400s to get the temperature difference to be the deciding factor. All right, so at the same temperature, we'll use Graham's law. And then if we're at different temperatures, we'll calculate RMS velocity. Any questions on the gas speeds business? Like I said, I know a lot of you did this in high school, so that's the good news. All right, we're going to continue our review of gas. Right? Talk about pressure. Okay, so this, we've already talked about pressure when we talked about atmospheric pressure in the liquid phase and all that good stuff. So pressure is the result of collisions. Right? And if we decrease the volume, we increase the frequency of collisions, which means we increase the pressure. So if you have gas in a cylinder and you've got a piston that you can lower it, right? As you lower that volume, you're going to increase the pressure. That's gas compression, right? That's the idea behind compressing a gas. If you are putting air in your tires, right, you're compressing that gas. You're increasing the pressure. So your handout that I gave you has the units of pressure on it and their conversions. So I will give you these conversion factors on your reference page or on the test, or on the quiz. I'm not going to make you memorize them. Some courses may make you memorize them. I'm not going to make you memorize them. But you need to be able to set up a conversion factor. That's important. Okay, so if I gave you millimeters of mercury and I asked you to convert it to atmospheres, you would need to be able to set up the appropriate conversion factor to do that, right? The unit you want to go away goes on the bottom, unit you want to keep goes on the top, multiply straight across and divide. So I won't make you memorize these conversion factors, but you would need to know how to do it. Okay. This is a table from a different textbook. It's not our current textbook. But the thing I want you to notice here is that you don't see PSI on here anywhere, right? Pounds per square inch. It's not a metric unit. That's not a metric unit. So how many of you have done gas laws at some point in your history? I think most of us have, right? So the variables that we're looking at in gas laws, pressure must be in atmospheres. So that means that if I gave you the pressure in kilopascals, you need to convert it to atmospheres. Volume must be in liters. N, we have already seen lowercase n, right? That stands for number of moles. Kelvin temperature, and then R, here's our other R. I told you there were going to be two R's. This is the gas constant, 0.08206 liter atmosphere per mole Kelvin. Atmospheres, liters, moles, Kelvin temperature, and then R is our gas constant. Notice that the units of R will cancel out all of these other variables, right? So if you forget what unit one of these needs to be, just look at the units of R. Oh, okay, volume must be in liters, pressure must be in atmospheres, number of moles, temperature must be Kelvin. So if you forget that pressure needs to be in atmospheres, you can look at the units of R, and that'll remind you. Okay, so those are the two different R's. Okay, so make sure that you're using the correct one. Now they're all the same number, they're just converted to be different units. Okay, that's all that is. It's the same number, we're just, when we convert the units, the value changes. Now you've probably seen these gas laws, I left one off. Right, you've seen these in high school. I'm assuming everyone in here did this in physical science or high school. Boyle's law and Charles' law and Avogadro's law and Gay-Lussac's law and all those great gas laws. Those are all fantastic, but we're not going to be dealing with them at all. 0%. The only gas law that we care about is, I'll come back to STP in a second, the ideal gas law. That's the only gas law that we give a rip about. So if you did Charles' law and Boyle's law and Avogadro's law and Gay-Lussac's law, all those other ones in high school and you excelled at it, great. That's awesome. But we're not going to do them in this class because the only one we care about is the ideal gas law. PV equals nRT. PV equals nRT. I'll go back to STP in just a second. Ideal gas law is the only one we're interested in. Okay, so atmosphere pressure, volume in liters, N is number of moles, Kelvin temperature. And now STP. Remember I talked about standard conditions for thermodynamic calculations? And I said that's different from STP. Okay? When we're talking about STP in gas calculations, pressure is 1 atmosphere and temperature 0 degrees Celsius. When we were doing our thermochemistry calculations at standard conditions, right? All of these are at standard conditions. Standard temperature there was 25 for thermodynamic calculations. But here, when we're talking about gases, temperature's 0 degrees Celsius. So are we at STP right now? No, we're not. Right? Temperature in here is not 0. Temperature's in here at about 24, 23 and change. Okay, so we're pretty darn close to standard pressure, but we are not standard temperature. Now, in terms of thermodynamics calculations, we would be, but not STP. Okay, so all those other ones are great, but we're not going to be dealing with them. Now, if you want to, go back and review those, here are the pages in your textbook where you can, But I will not put Charles' law, Boyle's law, Avogadro's law on a test. They're not going to be there. Okay, the only one that I care about is the ideal gas law. So let's do this one together. A 16-liter oxygen tank is pressurized to 37 atmospheres when the temperature is 38 degrees Celsius. How many moles are in the tank? Because here's a nasty little preview of things to come. If we get number of moles, then what do you think we can do? Everyone's favorite word that begins with S. Stoichiometry, that's right. We're going to do some gas phase stoichiometry. So, if we've got a 16-liter tank, pressurized 37 atmospheres, temperature of 38 degrees Celsius, how many moles? Well, I always recommend listing out your variables and converting any units as necessary, right? Pressure is atmospheres, so we can leave that alone. Volumes in liters, we can leave that alone. R is a constant. Temperature was in Celsius, so we need to convert that to Kelvin. Right? So if we've got the ideal gas law, PV equals nRT, we want N by itself, right? We're rearranging the ideal gas law. Number of moles would be PV over RT. You could also just plug directly in here, do your algebra just like normal. Either way works, you'll get the same answer. We're rounding our answer to two significant figures, so 23 moles. 23 moles is a lot, but it's a 16-liter tank. That's a large volume too. Ideal gas law. So Charles' law and Boyle's law, all those are great. They're not going to help us do stoichiometry. Ideal gas law, that'll get us some stoichiometric fun. It'll help us calculate density. It'll help us calculate all kinds of great stuff. All right, you do this one. A sealed 589 milliliter container contains 14 moles of fluorine. It's under 27 atmospheres pressure. What's the temperature in this tank? Of course, that's a very small tank. I guess I should say flask. All right, let's talk about this one. So we've got a lot going on here, right? We've got a volume that's very small. Right? This is 946 milliliters. So that means that 589 is about right there. Right? That's not a large volume we're dealing with. 14 moles is a lot. 27 atmospheres pressure is a lot, right? Those are all, that's a big number of moles, that's a high pressure. And it's a small volume. So intuitively you might go, oh my goodness, the temperature is going to be like through the roof, right? But it comes out to be a very low temperature. Why? Why would this be a low temperature? How are you going to cram 14 moles into a volume this much and have 27 atmospheres pressure? It's got to be, I mean, your pressure is going to go up just from the sheer fact that you've got 14 moles in such a small volume, right? That's what's going to result in your pressure. So these particles are going to have low energy. In other words, you're probably not going to have a gas anymore. You're probably going to condense it. It's probably going to be forced to condense down to the solid phase even. I mean, you're going to have some difficulties achieving this, right? This would not be something practical that you could just go in the lab and do. To get to 27 atmospheres pressure is going to take a lot of effort. To get 14 moles in there, and that's such a small volume, it's going to take a lot of effort. So something's got to give. You're going to have to decrease the temperature way down. Yes?
So why did the number of moles like switch? Like the temperature was like in the previous problem, the number of moles for 25.
Right. So I'm just rearranging. PV equals nRT. To get T by itself, you divide both sides by nR.
Okay, because you were looking for temperature 6.1.
Right. In the previous one, we were looking for pressure, weren't we? We were looking for number of moles. Yeah. So if you don't like rearranging it and then plugging in, you could plug it straight in right here and just do your math like it's regular algebra. It works either way. All right, try this one. Calculate the volume of 1 mole of argon at room temperature, which we'll assume is 25 degrees Celsius, and a pressure of 1 atmosphere. pretty close to the conditions we're under right now. We're not quite 1 atmosphere pressure. We're not quite 25 degrees Celsius. We're pretty close. All right, let's go over this one. So this is a lot more likely than our previous one with 14 moles in 589 milliliters, right? That's not something you could do in the lab. This is something you could do in the lab, right? Because we're at pretty close to 25 degrees Celsius right now. We're pretty close to 1 atmosphere. So if there's the ideal gas law, right? To get volume by itself, I came up with, when I have 3 significant figures, 24.5 liters. Do we agree? All right, so here's some pictures. These are real pictures. They're not the most recent pictures. But hey, it's almost 7 years ago to the day, I think 2010. This has happened to me a couple times in my life. I found these in my car. And this one's blown out on the side. The top's still sealed. The bottom's still sealed. So what happened here? I found these this was found in November. That's when I discovered it. And where I found it is in the space between, you know how you can lay down the back seat in your car? I found it in that interspace between where you lay down the seat and where you get to the trunk. You know, so you can open the trunk from this side and you can lay it down this way, right? So I found it in that space in between. So what happened here? Wasn't the temperature drop, because I didn't find a chunk of ice or a chunk of frozen soda anywhere. What happened is the opposite. Well, what happened? It exploded, right? So if I had this can of soda in here, and what happened is we had gone to see my family. We had like a barbecue or a cookout or something with a whole bunch of cans of soda. And we said, hey, we'll take some of them home with us, right? So we threw them in the trunk. We drove home. It's a long drive home. And that was during the summer. And one of them just rolled into that space in between. And I didn't know about it, right? So we're talking summer. You know, temperature in the car gets really hot, right? And so the gas in here starts to expand, and then it just explodes. I'm so thankful I wasn't driving when it happened, because I would have had a heart attack. But this has happened not once, it's happened at least twice. I found one, this is Diet Coke. I found one with RC a few years ago. That would have been like 2013, 2014. And it looked exactly the same. And so in this particular car, it gets hot enough that if you leave the can in there, it'll explode. I mean, because I never found any liquid. I never found any. It just got so hot, it vaporized as soon as it exploded. And I was never in the car. I never actually witnessed it. So kind of interesting. You can, another ideal gas law, true story, happened to me. You can go talk to Dr. Day about this, because he was there. So if you're going to see him today, you can ask him about it. When we first moved down here, which was a long time ago now, about 2010, 2011, we'd moved all our stuff, and everything sat in the garage for about a year. My bicycle, I like to ride my bike. And it sat in the garage for about a year, and then it was one of those springs where it was like a 90-degree spring day, you know, like it went from being 50 degrees to like 90, you know how it is. And so I got my bike out, I'm like, yeah, I'm gonna go for a ride, this will be great. And I'm riding, and something goes weird with one of the brakes. And I'm near where he lives. I'm like, well, I'll pull over to his house. I'll use his phone, call my husband to come get me, because I didn't have my cell phone with me. Ride my bike over, standing there talking to him, talking to his wife. And all of a sudden, my tire on my bike just exploded. I mean, it just completely exploded. Like, it sounded like a gun going off. The inner tube exploded first, and then the outer tube exploded second, if you've ever seen the inside of a bike tire. And so what happened? What happened? Explain what had happened there. That would be ideal gas law 2. Bike sat in my garage for a year, didn't get touched for a year. So what do you think that did to the tire's integrity? Well, I made a weak spot, right? It was sitting there for over a year. Maybe it even, you know, made it flat on one spot. Who knows? It was weak. Rubber got weak there. And then I'm riding on the road. It's a 90-degree day. The road's going to be really hot. So what happens to the gas inside the tire? It expands. It starts going faster, right? And if I've got a weak spot on the tire, tire can't handle that new pressure, and it just exploded. Thankfully, I was standing next to the bike and on the bike when it happened. So very thankful. But look for the ideal gas law. It's all around in the real world. Hopefully you don't ever have an exploding can in your car while you're driving. That would be a very scary experience. Hopefully your bike tire never explodes while you're on it. But it's all ideal gas law. So that's where we're going to stop for today.